Humanity has sent spacecraft to nearly every planet in the solar system. A rover is rolling across Mars right now. Pluto was photographed from less than 8,000 miles away, but there's one direction we've barely touched. Straight up, above the sun, out of the thin plane where all the planets have been circling together for billions of years. Physics has its reasons. Every spacecraft leaving Earth carries something it can't leave behind. The orbital velocity of the planet itself, nearly 19 miles per second, locked in a relentless sideways race around the sunday. To escape that plane, a spacecraft first has to deal with all of that lateral momentum. And that's the price that makes a point just a few million miles above the sun's pole, potentially harder to reach than Pluto, sitting at the far edge of the solar system. This is the story of the invisible disk that's been holding us in place, and what's waiting on the other side of it. Let's start with the moment a rocket leaves the launch pad. Most people picture it like this. A massive machine punches through Earth's gravity, breaks free into empty space, and from there, goes wherever it wants. But the reality is far more complicated. A spacecraft doesn't begin its journey from a standstill. It launches from a planet that's already hurtling around the sun at nearly 19 miles per second, roughly 67,000 miles per hour. That motion transfers to the spacecraft from the very first second, and there's no way to leave it behind on the ground. For most missions, that's actually a tremendous advantage. Heading to Mars, Jupiter, or anything else orbiting near the ecliptic plane, the flat disk where all the planets travel, a spacecraft just needs to adjust from the motion it already has. Earth's sideways velocity becomes a launching pad, and the spacecraft doesn't have to build all of that speed from scratch. The problem only shows up when the destination sits in a completely different direction, straight up above the sun, or straight down below it, perpendicular to the entire planetary plane. At that point, 9 miles per second of sideways motion stops being useful. The spacecraft is being pushed sideways when it needs to go straight up. Think of it this way. You're standing on a train, barreling forward at incredible speed. You want to jump sideways, perpendicular to the tracks. But no matter how hard you jump, your body keeps moving in the direction the train is going because you're carrying its velocity. To truly break free in that sideways direction, you'd need a force strong enough to cancel out the entire train's momentum first, and only then could you start building movement in the direction you actually want. In spaceflight, the real cost of a journey isn't measured in miles or kilometers, it's measured in delta V, the total change in velocity a spacecraft has to generate using its own engines. Delta V is the true currency of a mission, and it determines which destinations are reachable and which ones are simply beyond what current technology can pull off. Here's what the numbers actually look like. Sending a spacecraft from low Earth orbit to Mars on a standard Hohmann transfer takes roughly 3 to 4 kilometers per second of delta V. That's a large number, but well within the reach of modern engineering. Flying straight out of the ecliptic plane, which means cancelling out nearly all of that 19 mile per second sideways velocity inherited from Earth, and then pushing the spacecraft in a perpendicular direction, requires around 30 kilometers per second of delta V, nearly 10 times as much. Pluto sits more than 3 billion miles from Earth on average. A point directly above the sun's pole might be only a few 100 million miles away. But in terms of energy, reaching that point above the sun's pole costs far more than the journey to Pluto, simply because it sits in a direction where Earth's orbital velocity offers no help at all. And that direction, for most of human spaceflight history, has been left almost entirely unexplored. Humanity has observed the sun from a single vantage point, from the side, from near its equator, from within the same plane that Earth has been moving through all along. It's a bit like trying to understand the full climate of a planet while only being allowed to stand near its equator. You can measure temperature, wind, humidity, but what's happening at the poles, where the weather follows its own set of rules, remains completely out of reach. With the sun, the polar regions are anything but a minor detail. This is where the fast solar wind is generated from polar coronal holes, where the sun's magnetic field has a structure fundamentally different from the equatorial region, and where the roughly 1-year magnetic polarity reversal originates, the cycle that drives space weather across the entire solar system, affecting satellites, radio communications, and power grids on the ground. The first serious attempt to break out of that flat perspective came in 1990, when NASA and ESA launched the Ulysses spacecraft from the cargo bay of the Space Shuttle Discovery. Because flying directly to the Sun's poles was still energetically impossible, engineers chose an indirect route, sending the spacecraft out to Jupiter and using the planet's enormous gravity to bend its trajectory southward out of the ecliptic plane. After the Jupiter flyby in February 1992, Ulysses settled into an orbit tilted 80.2 degrees relative to the planetary plane, an angle no spacecraft had ever achieved before. For the first time in history, a human-made object had passed through the polar regions of the Sunday. Ulysses carried a suite of in-situ instruments, measuring solar wind, charged particles, and magnetic fields, and through that data, humanity made its first real contact with the polar environment in actual numbers. Like the first person to climb a mountain in complete darkness, you can measure the temperature, you can feel which way the wind is blowing, but you cannot see the landscape. A remote sensing camera to photograph what was passing beneath it, that was something Ulysses simply didn't carry. The next generation arrived with Solar Orbiter, a joint ESA and NASA mission launched in February 2020. Rather than a dramatic single slingshot out to Jupiter, Solar Orbiter took a far more patient approach, repeatedly flying past Venus, nudging its orbit a little further out of the ecliptic plane each time, slowly building up inclination over years. In February 2025, after one of those Venus flybys, Solar Orbiter reached an orbital tilt of 17 degrees relative to the Sun's equator. During the third week of March 2025, the first direct images of the Sun's south pole were transmitted back to Earth, from a spacecraft with cameras looking straight into the region that Ulysses could only reach through numbers. Our nearest star, after all those years, finally revealed an angle that no one had ever truly seen before. That new perspective, once opened, pulled an even bigger question into view, not just what the Sun's poles look like, but where the true boundary of the entire solar system actually sits, and what shape it takes. Scientists call that boundary the heliosphere, a vast bubble created by the solar wind, the constant stream of charged particles the Sun fires outward in every direction. As long as the solar wind remains strong enough to push back against the interstellar medium outside, the heliosphere holds together as a protective shell surrounding the entire solar system. Every planet, every comet, every asteroid, every spacecraft humanity has ever launched, all of it sits inside that shell. Beyond it lies a completely different environment, where high-energy particles from distant stars roam freely, no longer held back by the Sun's influence. For decades, the most widely accepted picture of the heliosphere was a giant comet shape, a rounded, blunt nose at the front, where the solar system plows into the interstellar medium as it orbits the galactic center, and a long tail streaming out behind. That image appeared in textbooks, in scientific papers, in nearly every illustration of the solar system you've ever seen, and for a long time, nobody had enough data to argue with it. Then in 2020, a study published in Nature Astronomy, drawing on data from multiple NASA missions, proposed something different. The heliosphere might look less like a comet and more like a deflated croissant, with two lobes curling outward on either side instead of a single long trailing tail. Not symmetrical, not smooth, and without the tail that had been assumed for decades. The Sun's magnetic field, it turned out, was funneling the solar wind flow into two distinct directions, producing a far more complex structure than the simple comet picture had ever suggested. The reason we still aren't certain is straightforward. We're living inside it. Trying to determine the shape of the heliosphere from within is like trying to sketch the layout of a room you've never stepped outside of. Voyager 1 and Voyager 2 are the only spacecraft that have ever crossed the heliosphere's boundary and sent back direct measurements, but 2 data points aren't nearly enough to trace the full outline of a structure tens of billions of miles across. NASA's IMAP mission is designed to improve that picture, mapping the interaction between the solar wind and the interstellar medium in greater detail by measuring particles streaming inward toward Earth from the heliosphere's edge. The data will be better, more detailed, and will almost certainly help narrow the gap between competing models. But IMAP is still an eye looking outward from inside the bubble, observing what comes to it rather than stepping outside to see the whole thing at once. That's a limitation only a genuinely different vantage point can overcome. A spacecraft flying high enough above the ecliptic plane could look back at the entire planetary disk from the outside, and for the first time give us a direct view of the true shape of the home we've been living inside, rather than piecing it together from fragments of data collected from within. The question that remains is how? Building a bigger rocket, carrying more fuel, that sounds like the obvious answer. But with a delta V requirement of 30 kilometers per second, that path is essentially out of reach for current technology. Orbital mechanics offers a different answer, and it's counterintuitive enough that hearing it for the first time feels almost impossible to believe. To fly above the sun, first you have to dive straight toward it. Not literally, but closer to literally than you might expect. The idea is called a solar Oberth maneuver, a technique rooted in a principle of physics that German scientist Hermann Oberth described in the early 20th century. The core of it works like this. The faster a spacecraft is already moving, the more orbital energy each unit of burned fuel produces. The deeper the gravitational well, the higher the velocity, and the more each second of engine burn gets amplified. The deepest gravitational well in the entire solar system, the place where a spacecraft can reach its highest possible velocity, is the point in its orbit closest to the sun. But to fall toward the sun in the first place, the spacecraft first has to deal with the 19 mile per second sideways velocity it inherited from Earth. One of the most efficient ways to do that is to fly out to Jupiter, perform a retrograde gravity assist to cancel out most of that lateral momentum, and from there begin falling freely back toward the sun, accelerating continuously throughout the journey. At perihelion, when the spacecraft is moving at its absolute fastest, the engines fire. The Oberth effect amplifies that burn many times over compared to firing the same amount of fuel at a greater distance. The result is a spacecraft that shoots out of the gravitational well with a completely new velocity and trajectory, including a component that carries it out of the ecliptic plane. The plunge toward the sun, paradoxically, is the launching pad for climbing out of the planetary disk. Of course, getting close enough to the sun to fully exploit the Oberth effect demands extreme heat shielding technology. NASA's Parker Solar Probe currently holds the record for the closest solar approach ever made, and its heat shield has to withstand temperatures reaching into the hundreds of thousands of degrees. A true Oberth mission would need to get even closer, and that remains an engineering challenge still under active research. The second path approaches the problem from an entirely different direction. A solar sail doesn't burn fuel at all. It runs on light. That sounds strange, because light has no rest mass. But in physics, photons still carry momentum, and when hundreds of billions of photons strike a large reflective sail every second, thrust builds up gradually. Small in any given moment, but continuous and inexhaustible as long as the sun keeps shining. The entire process unfolds in complete silence, light pressure accumulating day after day, year after year, slowly pushing the spacecraft out of the planetary plane. Two paths with two completely different rhythms, one violent and immediate, one patient and steady. A future mission architecture could combine both. Use a solar sail to work closer to the sun, build up a favourable position, then fire an Oberth burn at perihelion to launch the spacecraft out of the planetary disk at a velocity nothing else could achieve. As the spacecraft climbs above the planetary disk, the first thing that changes isn't what it sees ahead, it's what disappears behind it. The planets in our solar system don't travel through perfectly clean vacuum. They share their orbital plane with a thin layer of dust, the remnants of evaporated comets, debris from asteroid collisions, material ground down over billions of years. From Earth, this dust is visible on the darkest nights, appearing as a faint pyramid-shaped glow stretching along the ecliptic after sunset or before sunrise. Astronomers call it the zodiacal light. For astronomy, this dust layer is a permanent haze. It scatters sunlight, raises the background brightness of the sky, and masks extremely faint signals from the distant universe. Astronomers searching for the cosmic background light, dim galaxies at the edge of the observable universe, or atmospheric signatures from exoplanets dozens of light years away, all of those signals are being contaminated by zodiacal dust. A telescope positioned above the ecliptic plane would escape that haze entirely, looking out into the universe with a cleaner sky than any position inside the planetary disk could offer. The solar environment shifts as the spacecraft climbs higher. Near the sun's equator, the slow solar wind blows at around 400 kilometers per second, gusty and erratic, difficult to model and hard to predict. Further up toward the polar regions, the fast solar wind streaming from polar coronal holes can reach 700 to 800 kilometers per second, blowing steadily with a far cleaner magnetic field structure. The transition between those two wind regimes, where exactly it happens, why it happens, and how the sun's magnetic field shapes it, is one of the questions Ulysses touched on but never fully answered. A spacecraft passing through that region with modern instruments could measure that transition directly, kilometre by kilometre. But the most valuable thing might not be the data at all. It might be the photograph. In 1972, the crew of Apollo 17 took a photograph of Earth from about 28,000 miles away. For the first time in history, humans could see their entire planet at once, a small blue marble suspended in darkness. That photograph didn't produce new scientific data, but it changed the way millions of people thought about Earth, about its fragility, about the true boundaries of the place they called home. From high enough above the ecliptic plane, the solar system would appear in a way no textbook illustration has ever captured. A thin disk of orbits, dust and planets spread out below, the sun at the centre, everything surrounded by the darkness of interstellar space. That photograph doesn't exist yet, and it remains one of the missing images of humanity. Looking back at all of this, one thing stands out. Humanity has travelled extraordinarily far across the solar system. Voyager 1 is now beyond the heliosphere, more than 14 billion miles from Earth. New Horizons flew past Pluto and kept going. Parker Solar Probe is reaching regions near the Sun that nobody dared imagine touching. But nearly all of those journeys happened within the same plane. The thin disk where the planets travel together, where Earth's orbital velocity is always ready to serve as a launching pad. The vertical direction, above and below the Sun, remains the most expensive, the most difficult, and for that reason, the least explored. The Sun's poles are still incompletely understood. The true shape of the heliosphere is still being debated, and the photograph of the solar system seen from above still doesn't exist. Sometimes, to truly understand a place, you don't need to go farther. You need to stand somewhere else and look back. Space isn't just near and far. Space has perspective. And sometimes a new perspective is what changes everything. Not the distance, not the speed, but the direction that no one has ever looked toward. If a mission to fly directly above the Sun ever becomes real, which path would you choose? A solar sail, slow and steady, using light itself as its engine, or a violent O-berth dive toward the Sun to catapult out of the planetary disk?